in that there are 24 ones. So CIDR notation is just a representation to show a network mask. So here you can see CIDR notation, and this part is network mask encoded in such a format. So in IPv4, there are a few subnets that are reserved for specific purposes. One of those networks is designated for loopback addresses. So if you would ping on your PC 127.0.0.1, you will get the response from a virtual IP address, which is your PC itself. And this subnet is a bit wider, not just 0.1. Also, there's zero-conf technology, and the logic behind it that Windows system then is booted up, and when that system does not have IP address and is not connected anywhere, it will just generate randomly IP address from this subnet. So if you will have two PCs in the same network, there's a big chance that those two PCs will be able to talk among themselves because they will be in the same subnet. Also, there are subnets reserved for anycast when IPv6 is translated into IPv4, multicast. So the main message is that there are subnets designated to some purposes, and some subnets are reserved for local networks. So from class A, it's this one, B goes here, and I guess your favorite one is C class, starts with 192.168. And those numbers might look strange for a person who does not consider binary to be behind that, because anybody would expect like this to be like 100.10 or something like that, like something decimal, but those numbers do come from binary. That's why are as they are. And IPv6 is a huge address. So IPv4 had 32 bits, and IPv6 has 128 bits. So really long address, and it is represented in hexadecimal. So I guess that you know few of IPv4 addresses, but to know or to tell over the phone IPv6 address is too much of a task. It's close to non-human unreadable. And also another thing to consider is that zeros are being represented in a few separate forms. So one of those forms is just changing 4 zeros into single one, and you can go even further, skip those zeros. So anybody would understand that more zeros are between most semicolons. No, how I was called, like with punctuation. There should be all the zeros if you see two of those. And the number of IPv6 addresses is huge. It's much more bigger than the number of people on planet Earth. I'm not sure what's the population of Earth at the moment, but most likely we will have enough IPv6 addresses for a really long period of time. And currently, all the IPv6 addresses that are being used for host addressing come from this global unicast group. And most of the address space is reserved for future cases. So IPv4 has really limited number of addresses, and the prediction was that those addresses will expire on 2010. But I think that all of you, or at least most of you, do use IPv4 addresses currently. So we were able to save IPv4 addresses, and IPv6 is still not like dominating internet protocol. Again, the problem, where did we lose all those IP addresses, is that number of mobile devices is really huge. Devices are turned on constantly, so devices use that IP address. Internet expands, and now with those projects that Google and then SpaceX does to do like global internet, you can imagine how the number of internet connected devices will rise. And at the beginning of internet, addresses were used really inefficiently. So that's what led to lack of IPv4 addresses. But there are technologies that allow to save the addresses, like network address translation, and local area network has those LAN IP addresses, and those get translated into single one global IP address. So we are saving there. Also, dynamic host configuration protocol allows hosts that are turned on to reuse the same IP address. Also, there are name-based virtual hosting technologies that allow to tie a globally addressable domain name to some internal IP address. Also, IP address issuing is really strict nowadays, and also we managed registrars managed to get some IP address blocks that were given away at the beginning of internet, those large ones. And regional internet registrars are 5 of those. In Europe, we do have RIPE. RIPE is Registrux IP Europux, something like that. Pardon my French, but it means like IP European register. I guess I showed the slide to you on our first meeting. All internet IPs and addresses are being managed by IANA organization and ICANN in particular. So the organization is not flat. It has like departments, groups, committees, and so on. And now let's talk about domains. So domains are symbolical addresses, and they are hierarchical. So at the very top, there's a root. It's a dot, but we do not put a dot at the end. That way would not work, but logically there's the dot, then top level domains, first level domains, and so on. So top level domains are at the very end, and to access the resource you do need to know fully qualified domain name, and then you can access that resource. So domains are defined in domain name DNS servers, and those DNS servers have domain zones, and those zones have entries with a name, type, then time to live value, how long this entry is valid. So every domain has a list of such resources which are put in the specific format, and that resource record also has type value, and type values are these. So if it's A, it's IPv4 address, 4A is IPv6 address, CNAME is like another name of the same of one of those the symbolic names. So like www.vgtu.lt, and we can put like CNAME like Eimantas.vgtu.lt, and the CNAME Eimantas will point then to www. You understand the purpose. Just sometimes you need different names for the same thing. Marketing campaign, some more complicated architecture, there are cases when you need it. Then MX is mail exchange record, name server. There are defined servers which are responsible for that domain. And then start of authority. He has a list of values like TTL and other stuff, which is not the name itself, but are values for the whole domain record. And also another two of those, pointer and server records, are for translating back. So you can translate not an IP address from DNS domain name, but vice versa. You can provide the IP address and get a domain name. So that is needed for multiple cases. One of those is how mail servers fight to spam. They do reverse lookup and ask, let's say some server introduces that it represents some domain. Then the receiving mail server asks IP such and such, which domains do you serve? And then compare the values. So here's the example of DNS zone record. There's start of authority with all the refresh, expiration values, name server entries, mail exchange. So which resource serves mail. Then can be text records and A records, which tie IP address to a name, and also where do you have a CNAME. So is this new to you guys, or were you familiar with DNS stuff? It's new. Okay, so we can look around a bit. So I'm using here my corporate DNS server. We can set the server DNS server we want, and then let's say if we look at what entries are where for VG2 LT, we can see like this IP provided, but we can change type. Remember types like MX and so on. And here we get more information. We do have name servers, so those two servers are responsible to provide the information regarding VG2 domain. Also, we do have a server which does mail. So mail server is tied to the domain. So there's no magic when you say send mail to some domain. DNS has entry, which server needs to process the mail. Also, here are like IPv6 address, as you can see, and also there are other values. Those are text values, and SPF stands for Sender Policy Framework, so it limits which servers can send mail on behalf of the VG2.lt domain. So that's in short, and also I think you should look a bit deeper. I guess there are some links on Moodle, because DNS is a really important one. And the dot, those root domains, yes, one of root domains, are the major ones, which point to top level domains. So there's a list of root level domains, and those are represented by a letter. And the magic is that single letter is being represented by a number of servers, and those servers are dispersed in the world. So sometimes there are discussions what to do, how internet can be turned off, or on the opposite. If some terrorists would like to turn the internet off, how it would be possible? So the answer is by turning off those root DNS servers. But as you can see, there's a number of those, and the routing to those servers is being done by Anycast. So network equipment knows how to reach those DNS servers. And like one more time, if you missed the logic, when you try to resolve some domain, at first your browser looks for that domain in cache file, and in cache file that domain gets cached when PC boots from a hosts file, so you can define it by hand, and also then some resolution is done. And that cache lives for a set amount of time, which is set in that DNS record. And if the name is not cached, then your PC looks for the IP address in the first DNS server, in caching DNS server, which is usually your router. And if it's not there, the journey starts. So at first, the query comes to those root servers. Remember, those multiple root servers, and the query comes to geographically closest one. And the question is, let's say you want to resolve www.cs.colorado.edu. So at first, the question is, who is responsible for edu domains, educational domains? And you get the response. Go to this IP address. When you go to this IP address you just got and ask, who is responsible for Colorado domain space? You get a name of those name servers. Then you go to that name server and ask, who is responsible for CS, and maybe you know who is responsible for CS www. And then you get the IP address and it gets cached in your closest DNS caching server, your local home router most likely, and gets cached in your PC. So that's what I wanted to tell you about IP addresses and domain names. Do you have any questions there? If not, let's talk about some major protocols. So I guess you looked at the material which is on Moodle. So I really encourage you to do it, because that way it would be much more efficient for you to learn and you get material faster. Now let's talk about major protocols from TCP/IP protocol stack. About Internet Protocol, Transport Control Protocol, User Datagram Protocol, and Internet Control Message Protocol. And to understand the protocol, for me, it's best looking at the header structure, because if protocol has lots of features, the header is complex. There's lots of things to be defined there. If the protocol is simple, straightforward, then header most likely will be really simple. So here you can see IPv4 Internet Protocol version 4 header structure. Version is being defined, header length. There's some bits reserved for prioritization type of service. Then the total length of the packet is defined here. Each packet has identification number. It is needed in a few cases. One of those is fragmentation. Then there's a part to do fragmentation. So if a packet comes to network equipment which cannot process packet that large, then that network equipment, router most likely, will want to fragment that packet. And there are like 2 bits being used, do not fragment. So that flag means it's 1 or 0. If it's 1, it's on. If it's 0, it's off. So if do not fragment it's on, then that packet will not be fragmented. And if a packet will be too large, it will be dropped. And another one is more fragments. It indicates that this fragment of the packet is not the last one. The first flag, the first bit, is not being used and in one RFC's request for comments standards, it was called evil bit. So the joke behind that was that if you're doing something evil, you need to set this to 1. If it's normal, it should be 0. So normally this value should be 0. If it's 1, something strange is happening. So when fragmentation is being done, we need to understand where the packet is. So is this like a first packet, second packet, last packet, or whatever? So this being defined by fragmentation offset, and it's defined in bytes. How far away in bytes this fragment is from beginning. So we do values like more fragments and fragment offset and packet ID. And on the other side, we can reconstruct the packet. Then there's a value TTL, time to live. The name is historical. The idea behind it is to avoid loops. So the highest value there is 255. And each network appliance, when packet traverses internet, subtracts 1 from it. And when it's 0, it's being dropped. So you understand, the packet will not get in an endless loop. It will reach 0 and will be dropped eventually. So TTL value usually is not 255, 255, 255. It depends on the on the operating system. So if you ping something, so we can see that in my case TTL is just 47, right? So I cannot go further than 47 hops, than 47 routers. Then my packet will be dropped. This is being done for efficiency. Then all the headers usually, or I don't know the case, then it's not true. All the headers have defined what's inside the packet, what protocol is inside the packet, because host needs to understand how to process the information that is inside. So this header tells how to process the data inside, what packet is there. And the header checksum, just to check that no errors came to be. And then two most important things for IP, for network layer, is IP address. So it's source IP address and destination IP address. So network layer has IP addresses to identify sender and destination. And there are routing tables which define the networks that those routers know about, and that helps for the packet to traverse through the network. So in this picture we do have FTP client communicating to DNS server. There's a number of IP addresses, the number of MAC addresses, and like one thing that I wanted to show you with this example, that then the packet traverses the network, sender IP and receiver IP are the same, right? Because the sender is the sender, receiver is the receiver. But MAC addresses do change, because you need somehow to get the packet from the client to the router, from one router to another router, from that router to the destination. So sender and destination are defined by IP addresses, and those IP addresses do not change. But routers then process and pass the packet through the network, communicate and switch, connect using their MAC addresses. I hope that I did explain this somehow in an understandable manner. Like, I don't know how about you, but like for me, it was like really interesting. So, okay, there's a sender, there's a receiver. How that packet travels through that large of internet? So the answer is that MAC addresses, those data link layer addresses, closer to physical addresses, allow that packet to travel through internet, changing those MAC addresses, but not IP addresses. Here's a picture about packet fragmentation. So if a packet is too big, it will be fragmented. Then IPv6 header looks like this. As you see, source address and destination address really need lots of space here. Then there's version, priority for as you remember, IPv4 had the type of service, so priority is used also. Then label, length of the header, next header, and TTL is replaced by a more understandable name, hops limit. How many hops can the packet go through until hop limit, hop count reaches 0 and the packet is dropped? So the header is simpler, but the thing is that it's because it has next header. So in IPv6 you can have multiple headers based on the functions. So there's always main header, but you can have like routing, fragmentation, authentication, and other headers. If you need to do something with the packet, additional header is simply being used. Then here's the concept about sockets and ports. So a single host can have different protocols running and different application servers running there. Because despite the same IP address, there are different ports used and different protocols used for different services. Yeah, so that's the reason why on the single server you can run, that's one of the reasons why you can run multiple services on a single server. Then let's talk about user datagram header. And UDP is connectionless protocol, best effort protocol. This means that there's no guarantees that information will be delivered. And it has source port, destination port, length, and checksum. So really simple header, but as you can see, UDP is already transport layer protocol. It adds port information. Okay, network protocols had IP information. Transport layer adds information about ports. So UDP is really simple protocol. ICMP, Internet Control Message Protocol, is also simple one, and it has type and code. It does not have ports. It has type and code, and that combination defines what kind of the message is being sent. So UDP has no means to communicate back if something bad happens. So the server, let's say some UDP port is closed on the server, communications comes to that closed port, then the server will answer with ICMP packet telling that this port is being closed. So there's some interconnection, not interconnection, but like the server, the service is using ICMP to help UDP, to help like the sender to get information on what's happening, because UDP does not have such a means. And the ICMP uses IP protocol. So I guess you should consider it to be transport level protocol, transport layer protocol, but it is not. It is considered to be a network layer protocol. Yeah, it's just a historical thing. And those type and code combinations define what's happening. So here are those combinations. So there's only type, and also there are codes. So when you ping something, echo request is being sent and echo reply comes back. So there's a number of types and codes that allow applications as ping or application as traceroute to function. That's the idea behind the Internet Control Messages Protocol. The last one is TCP, Transport Control Protocol. And as you can see from the header, it has more than previous protocols. So this protocol has more features. There's source port and destination port as it was in UDP. And the TCP is connection-oriented protocol. This means that at first you make a connection and only then data is being sent. And also if data is being lost, it's being noticed and the data is being resent. So those features are possible because of the sequence number and acknowledgement number. Other parts of the packet is header size, which here is called data offset. Also, some part is reserved. Also, there's like a space for flags. Again, flags is a sequence of bits which are on or off, 1 or 0. Those two flags are to indicate congestion. If some part of the network is being overcrowded by packets, to signal that those flags are being used. Then here's agent, and if agent is on, here is a value how much of the data, how many bytes is agent. So the idea was that let's say admin is doing some work and something went wrong, and then administrator wants to press Ctrl+C to cancel the task. But if there's no, like, you cannot put sense of agency in the TCP segment, you cannot get through. So that's how agent came to be. Then acknowledgement and synchronization flags are here. We'll talk about those real soon. Push is that all the content from network interface card was pushed to the network. Reset is to abruptly finish the communication. And thin flag is gracefully finish the communication. So if you're downloading something, most likely push and acknowledge flags will be on. Then there's a window value, how many packets can be acknowledged. We'll check it also in the next slides. So those flags and those numbers, sequence and acknowledgement numbers, allow to send data without losing part of the data, or if data was lost, then it's resent. So receiver gets all the data that sender sent. And as you see, TCP protocol data unit is called segment. So IP has packets, UDP datagrams, TCP segments. That's kind of a nuance how protocol data units are being called differently. So you want to send data, then you need to create the connection, and only then the data will be possible to be sent. And one more time to talk about the concept of sockets. So socket is pair of IP address and a port. So to make the connection, there's a socket on one side and socket on another side. And the connection is made between those two sockets. And also the same socket on the server can serve multiple hosts. So when you go to some web server, that web server does not have a socket for every client. So on this part is just one socket, but this let's say web server knows about all the hosts that are connecting to that server to be able to send the data back. Before the communication, before the data is being sent, communication needs to be established, and that's being done by triple handshake. At first, the client sends to server SYN packet. SYN means that SYN flag is on. Yeah, all other flags are off, SYN flag is on, and there's a sequence number. Then server replies with SYN ACK, those two flags are on, and then acknowledge number is received the sequence number plus 1, and then generated SYN number. And then client responds with acknowledge, and it takes that SYN number that was generated by the server, and one is being added to it and sent back. So SYN ACK and SYN means that SYN flag is on, acknowledge means acknowledge flag is on, SYN ACK means that both flags are on, and here's sequence number and acknowledge number. So I get a sequence number, then I acknowledge that sequence number. So I put it here and add the number of bytes that I did receive. So triple handshake, no data is being sent, so just one is being added there. Did I explain it okay, or do you want to talk more about triple handshake? Silencio vidatur confessio, as the people who spoke that language were telling. So then let's move. There are different states in TCP. So the connection at first is closed when some servers is listening, when SYN-SYNAC ACK connection is established, when data is being transferred. You are browsing web, watching YouTube, whatever. When there is a time to close the connection, it can be done abruptly by just sending reset, and that's it. Or this can be done by FIN. Sender closes the connection, receiver closes the connection, and the connection is being closed. Also, I mentioned the window size. So there's sequence number and acknowledge number, and window defines how many TCP segments with sequence number can be acknowledged. So you can imagine if you just acknowledge every segment, it's a bit pain. You get one acknowledge, get second acknowledge, it's slow. So the window allows to send the number of segments and then acknowledge those segments, and that's fine. The thing is that if the connection is really good and you do not lose any of the segments, then the window can be wide. The window means that all those segments in the window with those sequence numbers can be acknowledged. If sequence number is not in the window, it cannot be acknowledged, it's dropped. So if a connection is fine, window is wide, data is moving fast, and those segments are being acknowledged. If the connection is poor, some data is being dropped, then it would be better to have smaller window, because if the window is large, half of the stuff is being dropped, then it needs to be resent. It's complicated. It is better just to send a smaller amount of segments, and only then those segments make it to the receiver to send other segments. So that is being done by the window. Window size can be adjusted automatically based on the quality, based on how good communication goes. So window size defines how many segments can be sent without acknowledging. And not every segment needs to be acknowledged. There can be selective acknowledgement when all the segments from this till that are being acknowledged with a single acknowledgement. That's kind of a good thing to make communication effective. And that's what I wanted to tell you about TCP. Do you have any questions regarding all those 3 or 4 with IP protocols?
No, they were clear. Thank you.
Cool. Do we have any other topics then?
Sir, when do we need to submit the topics? Like, we need to pick a topic.
Yes. As faster, the faster, the better. So what topic are you thinking about?
Sir, there's like a deadline on each date of the topics, right? And these topics, like, if I want to choose from the one of the protocols, like, to be honest, I haven't chosen yet because I had a bachelor thesis topic and I was picking a topic lately and I had lab works, so I haven't picked a topic up to right now. But I will today take a look and choose a topic. To be honest.
Sure, please do, because the time flies by. Then there's like holiday season, so the faster you choose the topic, the more time you have to work on it, and then most likely the better grade you can get during the presentation.
There is a deadline, like for when
There's no hard deadline, but there's a deadline when homework will need to be presented, and homework will be presented, and the grade will come, or the homework will be not presented, and there will be no grade. So the faster you choose a topic, the faster you can go to work on it, and
to make a research and present the topic that we have chosen.
Yes, that's correct.
Okay, super to Arch.
Good. Do you have any other questions? If not, then thanks, guys. Have a great weekend, and
you too.
meet you next week. Bye.
Get over.
Okay.